Okay, now I have a basic introduction of Professor Yin. Okay, Professor Yin now earned his PhD from University of Manitoba in Canada in 1999, and he joined the Hong Kong Polytechnic University in 1995, and he became the chair professor of the soil mechanics in 2012. And Professor Yin is the leader in the geotechnical engineering, and he had developed advanced soil testing equipment and fiber optic sensors and established large-scale modeling facilities for geohazard research. Okay, and today, his topic is also on optical fiber sensing technology for smart and monitoring of civil and geotechnical structures. Okay, please.
Okay. Thank you very much, Professor Wang. It's my great pleasure and honor to visit university and to meet my good old friends, Professor John Carter, Professor Wang, and Professor Huang. And also really glad to meet you all here. Okay, I give Professor Wang a few topics actually to select. He selected this one. Actually, this is not my best. I tell you, this is not my best work. My best work in other area. Professor John Carter knows that. Okay, other areas. Okay, so. But this topic is very practical, can be applied for different fields. So Professor Wang has made a good choice, okay, for many other people if they are not really in geotechnical area, okay? And you can see the title related to optical fiber sensor technologies and applications in different areas. Okay, first one, I want to give a brief introduction to a scientific principle of optical fiber sensor technologies. I would say the fiber we use for sensor, as far as I know, is a single mode fiber. And the core material is the silica, CrO2. And the core material is very small. You can see 9 millimeter, very small, but it's covered by other materials for protection. And this structure is still what we call the bare fiber. It's a bare fiber. The real fibers, maybe you can see for telecommunication, for application in the harsh environment, even with more protections, heavy protections. Okay, so this is a bare fiber. The core of the fiber on 9 millimeter. Second one is for the fiber. If you input a light in the fiber, I can tell you my background is geotechnical, not in optical fiber on the science aspects. Okay, so I'm learning in this area. So what I can tell you, my experience, okay, to share you my experience. The optic fiber, you see, if you input a light, the light and the fiber will have interaction, interference, will generate a scattering light. I tell my students, it's similar to a pipe. The water flow in the pipe will still have some frictions. The water and the pipeline have some frictions, generate some microwaves. Maybe you don't see, you don't care. But for the light in the fiber, people are really interested in the scattering of light inside of the fiber, because we can inject the light into the fiber. There's a scattering light. The instruments can read out the scattering light. Let's do spectral analysis. Do spectral analysis. For example, people do spectral analysis. If I know those are the names of the scientists or professors who first discovered this kind of scattering light, Raman, Brownian, Rayleigh, in their names, because they first discussed different type of scattering light. People do spectral analysis. This wavelengths, this energy light, then the peak, the shift of the peak on the tension, compression, or cool, or heat, then the wavelength will shift. The wavelength changes are proportional to the change of the strain or temperature. That's the point people are very interested in, especially engineers or scientists, very interested in the strain and temperatures, and people can see what's happening at this point. This is at one point. Okay, at one point, you can also do this one. And in some technologies, they can get scattered light continuously on the fiber, no stop, continuously. So people can then identify the strains and temperatures along the fiber continuously. This is what we call disputed sensor technology, is distribution. of strength and temperature along the fiber. It's actually very interesting, okay, to so many engineering applications. Another technology is to cut to the grading at certain points of the fiber. So to use the laser, okay, to the certain grading, then use the face mask, use certain lights to make a grading on the bare fiber inside the core fiber, make a grading here. At this point, then we can fix the lambda. Sorry, this is Chinese, the lambda. Can fix the lambda at this point. This length can be 5 millimeter, can be 10 millimeter, can be 3 millimeter, depends, okay? Fix the point, then you put a light inside, then you can also do the wavelength, the spectral analysis. And this peak is also related to the strain or temperature changes, the shift of this peak point. So all the fiber sensor technologies, I would say most, are depending on the spectral analysis, the shift of this peak. Okay, this is another technology just to fix a certain point. So then, okay, so this is a different technology. Okay, the fiber broad grading. So actually, in my laboratory, we have used 3 types of technologies. So actually, there are more than 3. I can tell you. Okay, but I used 3 technologies. Okay, one is fiber broad grading. I mentioned before. We fixed the gradient at a certain point, one line, but at different point we can fix. Then we can measure strength at the different point at one line, at one fiber line. Okay, different from conventional technology. Second technology is what I mentioned. This is a quasi-distributed because one line, multiple point for measurement of strength and temperatures. Another one is a fully distributed sensor technology along the fiber. No need to do grading, no need. There's a continuously to measure strength, temperature along fiber. Okay, that's the advantage. Okay, and I used this one before. We got equipment from Switzerland, used for more than 10 years. Now it's old and it's almost not working anymore. But the accuracy of this one not good enough. Recently, we bought 2 instruments from a supplier in China. What we call is OFDR, Optical Frequency Domain Reflection. And the accuracy is wonderful, this one. So that now my group all use this one, not this one. That's not good enough. You can see the strain accuracy, missed the one, 10⁻⁶, 1 microstrain is very accurate, not just for geotechnical structure, even for steel, is very high accuracy. Another thing people don't know is this is a fully distributed sensor technologies. Another thing very important to us is space resolution space, 1 millimeter to 2 millimeter. This is very important for some model tests. That means we put fiber on the table or on the rock specimen, for example, or rock specimen. Then you compress the rock sample. The rock will generate some cracks. So we can stick the fiber on the rock samples, then do the compression, then fiber can sense which location can start to have a crack. You don't have to know the crack, nobody knows the crack where to occur, right? But the fiber can sense, here more strain, tension or whatever, so crack will generate. So this is because of fully distributed. That they can identify the crackers at 1 millimeter resolution, space resolution. That's very good for the model test because the model test size is very small. So the accuracy is very important. So we now use this one. But in comparison, the Boolean scattering, this technology, you know, the resolution is a 10. This is one. Is a 10 times 10⁻⁶, 10 microstrains, not enough. And also spatial resolution not good. Spatial resolution is 0.3 to 0.5 meters. Only good for large structures. For small structure, not good enough. So now we don't use it anymore. Now we use mostly this one and this 2. Okay. I mentioned this fiber broad grading first one. Okay, I mentioned before we do the grading at a certain point, then inject a light. So we can do the spectral analysis. We can, under the compression, tension or compression or temperature changes, we can measure the change, delta lambda B. This lambda B is fixed, is a given parameter we know. Then we do the tension, compression, temperature change. We can measure the delta lambda change. But this delta number, the wavelength change may be due to strain, may be due to temperature change. Two factors can affect this the shift of the wavelength. So, and this strain related to strain, and the C epsilon is almost a constant. Is a constant, okay? This lambda we know, epsilon, C epsilon we know the strain, but we don't know the strain yet. Can also be affected by temperature. So CT is constant, lambda B we know. So here you can see temperature strain both will affect the delta lambda. The problem is how can we separate? Later I will show you a simple way to separate, okay? Here we assume temperature we know, make an assumption we know temperature, or in the room temperature change is 0. Then this one will disappear. But in some external environment, the delta T may change with the weather, doesn't matter. We can separate temperature, we measure temperature separately, okay? So here we assume temperature we know. So from these equations, we can get the strain. Because engineers, scientists, we are more interested in the strain. Strain are related to many other parameters I will discuss later, okay? So then we can determine strains by this formula, delta lambda B we know, this one we know, temperature we assume we know, this can be determined, okay? And one feature of multiplexer measurement is one fiber line. What we call quasi-disputed sensor technology is one fiber line. We can have multiple gradients, and so multiple points for measuring strains and temperature. Just one fiber line. This is totally different from conventional technology, like electrical resistant strain gauges or wiper wire strain gauges is different. Okay, for example, for wiper wire strain gauges or for LVDT, one sensor, one cable, 10 sensors, 10 cable. So a bunch of cables, you know what I mean? But here, just one tiny, very small size diameter fibers, we can measure multiple points. So it's very efficient, it's very compact, small size. Okay, so it's just a difference. Okay. Now this is a calibration. You know, the strain wavelength change is beautiful, linear. Oh, for sensor, this line should be linear. Okay, this is no problem, no question about that. Okay. Now, how to measure temperature separately? This is a very simple temperature sensor. They put a fiber in a small, tiny metal tube. This metal can be copper, aluminum, stainless steel, some other materials, and put the fibers inside. So the fiber is not in contact with the surface, or this one is not in contact with any structure. Just is like empty small tubes is a temperature sensor. So this fiber can feel the temperatures, but not glued on any surface, which may be subject to tension or compression. Just feel temperature only. In this way, we can measure temperature separately. Okay, so it's a very simple way to do this one. This is calibration data done by my students. Okay, the linearity is beautiful. Okay, I don't go details. For distributed sensor technology, I mentioned before, I used this instrument before, Brilliant, based on Brilliant scattering. Raymond, I will introduce a little bit. My collaboration professors in our university use this one to measure. This one is good for temperature. But recently, my colleagues in the same university use this technology, this scattering light to measure the gases, different type of gas. That's a new development I'm going to mention. Oh, by the way, this one is a fiber, just ordinary fiber. We want to measure temperature. We want to measure strain. If we want to measure strain, the fiber must be attached to the structure, very tight. So the fiber can feel the compression tension of structure. For example, want to measure the strain of this wood, you have to glue it on the surface. There are many different ways to glue. Okay, that glue is one way. Okay, and how to measure temperature? You can use the same fiber, but the fiber is in the empty tube, like an empty fiber metal tube, which can only feel temperature, not in contact with structures. So then in this way, we can separate the temperature. Okay, can be done very easily. Okay. So this based on Brilliant, the scattering instrument, we bought this one from Switzerland. Okay, so they can, for example, imagine we have big pipelines. You won't worry about pipeline defections or whatever, or crack, whatever. You can glue the fiber line on the pipes. Pipe is normally very long, right? This technology is good for the larger structures. Then any strain or any temperature change, the instrument can read. can be a few, can be tens of kilometers for a large, long distance, a large structures. I don't go details. But recently we use more of this one, OFDR, or OFDR. I mentioned before, the strain accuracy is 1 microstrain. The space distribution is 1 millimeter, 1 millimeter. Any tiny cracks they can detect. That's the beauty of this one. We have two instruments. My colleagues in structure units, they have about 3. My group about 2. Very expensive, very expensive. $1 million Hong Kong dollars, 1 million Hong Kong dollars. But it's very good for model test. Okay. Okay, one application. Very quickly. The optical fiber sensors, what optical fiber sensor measured directly strain or temperature. But in many cases, in geotech engineering, we are more interested in other parameters, deflection, loading, displacement or cracks, or pressure. Okay, we are interested in a wide range of parameters. Here is one way to use the strains we measured for the optical fiber sensors to find the deflection of a concrete dam in a model test. Concrete dam. This is concrete dam, the foundations. This is a model test. My student, this is one more than 10 years ago. They use a hydraulic jet to simulate the water pressure to push the dam. The dam will have a deformation, foundation will have deformation. You can see there are many LVDTs to measure the lateral movement. We put the sensors here in the tiny tube, like a solid tube here, solid tube here. You put the tube, and the tube like my finger, tube put it into here, drill a hole inside. We put the fibers, similar strain gauge, FBG strain sensors on this side, If this one have any bending, naga pin, okay, naga pin. Sorry, I have a naga pin, okay, naga pin. If a bending, if there's a bending, here tension, here is compression, but we can measure tension strain and compression strain. For the tension, compression strength, we can convert to lateral deflection. The principal equations for the converting is there's a formula in the bin theory. In the bin theory, okay, the strengths can be converted, can be related to deflection. So this is what we did for this small model test. You can see one is here, one is here. You can see some cracks. You can see the what we measure here for this part, and this one for foundation part, cracks is measured here. By this converting, okay, and we also compare all measurement with conventional LVDT data. They are very close, very close. There some people ask me, I have LVDTs. What do we need the optical fiber sensors? So I don't need the optical fiber sensor. For example, this one we don't need. What the advantage of optical fiber sensors? Optical fiber sensors in this design, we can measure the displacement inside the structures. LVDTs can put on the surface on lateral side, but cannot put LVDTs in the soils or in the concrete dam inside. But here we can drill a hole, put a bar, put it inside. You can imagine this is a two-dimensional dam. If a three-dimensional dam here, also some area you can also see, right? So the optical fiber sensors can measure displacement inside of structure like concrete or soils. This is the advantage of optical fiber sensors. LVDTs cannot do. Another case is we apply this technology to measure the sediment of metro tunnels. This is existing tunnel, number 2 in Shanghai. This is existing one. This line. This is what my group working in the tunnels after the operation of the metro line. This is another tunnel under construction. To excavation cross this existing one, and people worry about this operation or safety of a tunnel because another tunnel construct on the top, then the soils will be removed. So the tunnel really not going to go up, rather go down because the weight of the soils above removed. So we put a tube here, a pipe, like a PVC pipe. People put a sensor on the top, sensor a strain on the top, strain on the bottom. So if this one go up or go down, this one will bend. Similar to a bin, will bend. So we measure strains. From strains, we can convert to the deflection. So this is a calibration in laboratory. My students before we install this one, my student did the calibrations. And you can see the final measurement, calibrations. This is what we measured from all sensors. This is what we measured from using other technologies. It's a hill going up. So it's quite consistent, okay, by these technologies. Another application is the slope. I'll go details. Slopes in winter in Sichuan province after a big earthquake, 9.8 scale, and the slope is moving, and we have two boreholes. We install our fiber in place accelerometer designed by my group. Okay, designed by my group into there. We have conventional in place accelerometers, but here the in place accelerometers were designed by us. The sensor elements are fiber broad gradients. We installed this one and two boreholes, and we can measure lateral movement inside. This is what I said. We can measure movement inside rather than the surface. I'll go quickly. Okay. Another also good applications. You can see this is a concrete precast concrete piles, and the piles will put on the vertical. Of course, you can see the metal plates. They can be weighted together to form a long piles. The piles will be driven, not driven, but hydraulic jacking, jack into the ground. And we put you can see here the slot here. We put a fiber sensor here to protect the fibers. And one is on this side, another on this side. This is just one line, only one fiber line, but the multiple point. This is another side for double. So for make sure we can measure the strength more reliably. So this is another line. Then put on the top. Then this pile will be jacked hydraulically, jacked into the ground. Then the strain can measure the strain of the piles. Put it in the one direction. Then when they compress, you can imagine the piles the soils will provide side frictions, side resistance, and also the end of the piles we also have resistance. Shift the side and the end will end the resistance, and we measure strength only. So if we know distribution of the strength, okay, we can distribution of strength, then we can calculate the side friction of the piles by this technology. So we are more interested in the side friction of the piles, which are one important part of pile building capacity. If we know the total force, we know side frictions, then end bearing, the tips, the resistance at the end of the piles can also be calculated. So this is another way to convert strength to friction on the piles. What I want to say is we show you a few examples. Strength and temperatures are two basic parameters optical fiber sensors measured directly, but we are smart. That's all advantage. And the electrical people, they don't know it, and we know it. We know how to convert the strength to other parameters. That's what my group are doing. You know what I mean? My group is not good in the design of the instruments. They are doing this one, but we know how to apply it, an innovative way. Okay. Okay, another idea is we can use the fiber broad gradient sensors to measure earth pressures, water pressures, and recently also effective stress. I will show you a few slides later, not in this PPT. We can also measure pore pressure, earth pressure, total earth pressures, and also effective stress directly by this technology. Okay, and later. This is all designed by my group, my students, and calibrated and used in our laboratory. Okay, there are many. We can also design the sensors to measure the tilting. Okay, the tilting. Okay, this is a cantilever beam. Put the two fiber sensor over here. This is a weight. This is a dead weight. You can incline. Okay, do you have a pen? Okay, let me use. Do you have a pen? Okay, imagine. Okay, put it this way. Put it vertical. And this is a dead weight. You can this is incline like this one. Like this one. This is cantilever beam. This is dead weight. This one you have get a bending here. This is maybe this is a tension to the compression. For the tension compression with the average, we can determine the strength here. Then we can this one can be related to the tilting, inclination of this one. This is one simple design of the tail meter. Okay, and there are many other things I don't want to mention today. We don't have enough time. What I want to say is we can convert the strength measured by optical fiber sensors to many other parameters we are more interested in. in a smaller way, okay? There are many ways you can do. This is another way you can say this is electrical resistance strain gauge. And this is optic fiber sensors. Discrete sensors. This is fiber glass fiber reinforced polymer bar. Okay, used as a soil nails to stabilize slopes. And we did this one by one of my students. Okay, the one excavation. And this is for construction metro tunnels, metro box. And you can two. I remember two. Okay, two soil nails was monitored by this technology, by this soil nail. You can see all sensor can measure the tension in the soil nails, continuously. Actually, in this method, the fiber, we put a fiber along the rebar, GFRP rebar, then coated by cement slurry. The cement slurry will stick all together. So finally on the excavation, then we have the soil nails will subject some tension. Okay, you can see EL24, the one soil nail, another soil nail. So you can see here more tension here. Probably it related to sleep surface. Okay, more tension inside. On top and the bottom is small. So we can monitor the strength along the soil nails really easy, very good. Okay, another good applications is a recent work we have done to monitor the trees and the old stone walls in Hong Kong. I don't know the story. How to monitor the trees? That's quite interesting. Okay, we got this project, some kind of R&D project from the government, and some trees. 2018, if I remember, a big typhoon hit Hong Kong. Many trees fell down, and the government quite worried about all the trees, and also all the trees grow up in the stone walls. They want us to set up our system to monitor all the stone walls and the trees. How to monitor trees? We tried two sensors. One is a strain gauge. You can see the strain gauge here. You know, strain gauge here. Can you see here? Here, strain gauge. It's not metal because the Young's modular of the tree not really strong, so we cannot use the metal. As a strain gauge. So we use some high strength plastic. Then put the fiber bar grating with a tiny FBG fiber bar grating on here. Then use a nail to fix this strain gauge on the trees. Because when trees is subject to wind, okay, then we can measure the strain, tension or compression. That's one way. Another one is use altimeter. I mentioned before. You see this is dead weight. This is a cantilever beam. Use this too. Finally, we found that this one is better. Okay, this one is quite difficult. Okay, not very accurate. Okay, we try on altimeters. Okay, but it's good. It's a good project. And for the walls, this is a retaining wall. The plan view. This is walls. We put the PVC tubes on the wall surface, similar to the one we tried in the metro line, the tunnels. Put the tubes on here, then put the strain gauge on top. So wall is any moving, the beam will, this tube will have a deflection. So we can feel the wall is moving or not moving. Okay, that's one way. That's a way to do it. We install 3 systems on 2 sides in Hong Kong. This is one example to see the old stone walls, the trees. We put horizontal beams, the vertical beams, and the trees we install the altimeter and the strain gauges. Okay. Okay, you can see quite a number of trees. The whole system, I don't go details. The data can be transmitted to the mobile phone or PC computer and give you warning. We set up the whole system by my group. I don't go details. Solar power supply, the movement of the trees. You can see one good example is at one time, we had one typhoon hit Hong Kong. You can see the shaking and you can see the water deflection can be monitored in real time and give the warning. Okay, it's a very good, successful project. The one I mentioned before, optic fiber sensors, can also be used to monitor gases. Okay, actually, I have a long time collaboration with this Professor Jian. He's in this department. Okay, electrical. He's a chair professor of photonics. He's the guy design the sensors, design the instruments, work on the science part. I'm working on the geotech aspect. Okay, he's very good. He's very good. Okay, I don't go details. You can see he do all kind of things about the sensors. Very wide applications. Geotechnical application to them is nothing. They are interested in more complicated applications. Okay, so we are interested. We have our interests. Okay, they have their interests. But one thing I want to mention today is the gas sensors, and liquid gas. Okay, gas sensors, because we also encounter gas problems. Okay, on the ground or above ground. Okay, so he designed different sensors, optical fiber sensors to measure different gases. One question to me, actually, I didn't understand is how can you use laser to measure the gas? Especially the gases, you don't see that. Oh, you maybe can feel, but you really don't see which is which. Especially some gases are in the same room, maybe a number of gases. They can identify different gases in the black box, even the concentration. I asked him, okay, how can we do so? How can we do this one? He tell me for each gas, they have a unique spectrum. That's the identification of each gas. You can see here. For each gas, if you put laser through the gas, they can receive the signal to the processing, do the spectral analysis. They can do the spectral analysis, right? I mentioned also before. For each gas, they have a unique signature. So for this one, they can identify the different gas. Another, we got the resolution, they have a formula, can also design the other resolution, concentration. They can also design concentration. Okay, here you can see CH4, C2H2, HO2, CO1, CO2, they can identify. And he designed a special so-called nano based on Raman. You can see here, I come over here, maybe you can recall. You get based on Raman, night scattering, design a nano fiber sensor. Here is very small. It's diameter very small. They can say make it small, like a nano size. The gas, if you contact this part, you can put this like some put it together as a sensor with some holes. The gas can go inside, contact this part, then put a laser here. They put laser in. Of the gas contact, the laser out, they do spectral analysis. They can identify different gases and also the concentration. Designed by Professor Jian. Recently, we tried this one at a site in China. Okay, we got some funding for China very successfully. I say Professor Jian is the number one, top one, top two in this area. Okay, work together with us. You can see for different gases, they can measure what's the resolution of gas. Okay. 3 ppt, okay, 5 pp mean, 5 particle per million, okay, 5 over 1 million, okay, it's concentration. Very small concentration they can identify. You can see developed by him. I don't go details. He can design instruments, sensors all together. And why recently we tried this one for the gas, H2 hydrogen. We are interested in this one because I know some countries want to store hydrogen on the ground, and China also trying to do the same. That's why we have this collaboration. Want to store hydrogen on the ground. Use the mine used already, empty already. Is empty on the ground after extracting other mineral materials. It's empty to inject hydrogen inside, but they are worried about the leakage because hydrogen molecular weight is very light. Very easy to escape. So the leakage of hydrogen is a concern. So then we can use the gas sensors developed by Professor Jian for monitoring. You can see, put it here and store the hydrogen inside. Then they can monitor possible leakage hydrogen. We tried this one in China very successfully. Now, remarks and conclusions. Number one, we have to know advantage of fiber block grading. This is based on Boolean distributed sensors, or if they are based on relay scattering gas sensors. All these kind of sensors have a common advantage, immunity to EMI. That's the advantage, okay? For some cases, this is very important, okay? Also, multiplexing, one line, multiple point is already different from the conventional one, or fully disputed. One fiber, we know strength temperature 1 millimeter, 1 millimeter, high resolution in the space, okay? It's good, okay? High resistance, because the core material is silica, no metal inside. Okay, another one, compact profile, very compact in size and good accuracy. And the absolute measurement, what I mean absolute measurement is this one, because the most of sensors, optical fiber sensors are based on spectral analysis. Their signal, the signals are very stable. So if that is different from the electrical resistance shrinkage, different, okay? It's based on voltage change. But optical fiber sensors, most, I would say most, are based on spectral analysis, is very stable. So if you take the initial reading today, maybe 5 years or 10 years, the change accumulated can be very reliable, okay? A long distance can be 10 kilometers, 40 kilometers away, you can measure, can also do wireless data transfer, is also okay. If we can monitor different parameters, and today I show you good examples how to convert strengths to other temperatures. Difficulty, okay, today we still face some difficulties. One is a relatively high cost of the instrument. The cost of instruments still high compared to the conventional one. And also less fiber sensors or transducers available in the market. Mature product available in the market is few. Even though some conventional companies can sell optical fiber sensor now, but it's still very limited, okay? So less knowledge or little experience to use them is also some difficulty. Not everybody know it, so difficult to use, okay? Damage, the fiber is a problem, okay? Fiber is quite fragile, easy to be damaged. That's a problem we also face, especially in the harsh environment. How to protect the fibers is very important. If a line is broken, everything you will lose. Of course, we can find a way to solve the problems, but we still have to pay attention to this damage to the fibers. We have to pay attention to this one. Okay, here, no need to repeat. I mean, the development in this area is still very quick. So it's still, you can see many new works, new development in this area still going on. So I don't want to repeat. I want to show you another PPT. Thank you very much. And I take this opportunity to, I have no time to bound this PPT with another PPT together. I have no time because I travel a lot recently. I take this opportunity to introduce this application to you. How to use fiber grading sensor to measure effectors directly. So you know that. You know, before we measure effectors by measuring total stress first, you know here. You know, before we measure total earth pressures and pore pressure separately, use two transducers, then do the difference, and we get the effective stress. But now we can measure effectors directly. And how to do this one? If you remember, if we have a sensor plate on the side, we have a cover plate on the side. For total pressure, earth pressure, this plate, no holes. No holes. So on this side, then we have solid particles and water pressures. So this plate will fill the total earth pressures. But okay, make some holes here. Need the water to go inside, the water inside. So the water pressure here, water pressure will balance each other. Fully balanced. Then only particles acting on the plate. So this is fiber sensor here can only feel the bending of the plate, measure effects directly. That's the ideas. And okay, I know temperature compensation, Professor Richard Jardine. No. Richard Jardine also say I didn't express temperature compensation directly. You can put a dumpy fiber here to measure temperature separately. This fiber is not contact with the surface here. You can feel temperature only. So if any temperature changes, this one may be affected by strain and temperature, but we measure temperature separately. So we can deduct the possible strain due to temperatures. So finally, this strain gauge can feel the bending, and also the particle on the surface directly. So we can separate temperature, remote temperature effects. And sorry, and this is a real product, okay? Real product with the back is the hose, okay? We got the USA patents. and also China patents proof our innovation. Okay, we are first. We got 2 patents already. Not the one. I don't want to sell to you. I just want you know this. We are approved by the USA authority and China authority. Our innovation. What I want to say to you, and you can make it. Okay, and no problem. As not for commercial sale, just for to use you for your own use. You can make it. Okay, you can make it. No problem. Okay, have no problem. And we have recently authorized this patent to a company in China to make it. Okay, for commercial sale. Okay, we don't make it. There are another company do this one. Okay, thank you very much.